It's actually a mix of research and industry, maybe even more industry. It's okay, because I work for a company now. But so my name is Ilya Bayantin. I've been working with, I'm a data visualization engineer. I've been working with movement data for quite a while. I did some research on it. I worked for a design studio where we developed data journalism pieces, and some of them were about movement. Now I work for a company called Paralytics. What we do is we partner with telecom companies. They give us access to data on people locations. Privacy is a huge issue. We take it very seriously. What we do with this data, which is very noisy, very imprecise because it's based on like cell towers, we try to extract, build models upon it that would allow us to extract OD data on like large-scale movement of people. How many people moved from A to B at what time? And our customers are mostly mobility services, transportation agencies, cities. One of our investors is Deutsche Bahn, the German railway. So OD data, probably most of you are familiar with. We just have origin, destination, and count how many people, aggregated count numbers of people move between origins and destinations. The traces, movement traces, are not taken into account. There might be some attributes assigned to every flow. So this is how one of our dashboards looks like. You see movement across the whole Germany, aggregated counts. We use flow map as our main geographic representation of the data. The thickness of the arrows shows the number of people moving. And we have a range of filters which allow the users to filter by different attributes. So some of them are time related. The data sets we are working with are quite large and always growing because new data is added over time. So we have to meet the challenges of data size and also the complexity. Like when you work with OD data, that's a lot of lines between pairs of geographic locations. If you draw them all, it's too complex to read. So we need to, what we need to ensure that is, in order for our tools to be useful, is that the interactions are responsive and the visualizations are readable. And the solutions are like go into multiple dimensions. Like one thing is the visual techniques. We apply lots of small techniques in order for the flow maps to be readable. We sort the arrows so that the largest are at the top. We fade the colors out so that the smaller are almost invisible. We use blending so that the instead of transparency, so that the underlying map is still readable, even if you have thousands of overlapping arrows. We draw borders around the arrows so that they are not like making one huge blob of one color. We also use WebGL for rendering, which allows us to draw more arrows, but it doesn't really solve all of the problems because at some point you just have too many and it doesn't help. So we also use some adaptive summarization and filtering so that we show a useful summary of the data. And another dimension is that we have a fast database in order for the users to be able to perform queries and to explore the data interactively. We first present an aggregated summary of the data and then visualize it in some readable way. The user can form a different query to select a slice of the data or a different facet of the data. Then we visualize it again, and this is the interactive exploration. So first I will speak about the scalable visualization. So the flow map which we use, we actually open sourced the library for drawing this flow map. It's available on GitHub. But as far as I know, not a lot of people are using it, because the two groups of people who know JavaScript and people who want to visualize movement data, have a small overlap. That's why I developed a tool called FlowMapBlue. It's actually the URL of the project is FlowMapBlue, which doesn't require any programming knowledge. People can just, in order to visualize OD data as a flow map, people have to put it into a Google spreadsheet, and paste the URL of the Google spreadsheet into the tool, and then it will be visualized on the map. No programming knowledge required. And since the tool has been published, hundreds of datasets have been visualized, very, very different ones across all over the world. Some unexpected usages, like I didn't intend this to be used for trajectory visualization, but since it's so easy to fill the data into a Google spreadsheet, quite a few people used it to visualize trajectories. I didn't think of sewage system as a use case for the tool, but actually sewage is all about geographic movement. So some people used it to visualize sewage system. Some of the data sets are quite messy. This is bus travels in São Paulo, Brazil. And you see, like, here there are many stops going in both directions, which are very close to each other. And they are actually two separate locations in the data set. That's why you see like some empty circles which show lots of outgoing movements, and close to them filled circles which show incoming movements. But this is not super useful in this form. Also, this data set shows migration relocations in Australia. Australia is sparsely populated. There are some very dense areas. And here the largest flows are actually in the dense areas. They're very short and not visible here. That's why it's not very useful to see it in this form. At Paralytics, we also have dense data sets. This is not very helpful. So at some point I stumbled upon this library, supercluster, which is actually intended to cluster locations. Like when you have lots of dense areas with locations, they are clustered into one big point, and you see how many points are inside. It says, like the original creator of Leaflet developed it at Mapbox. And I thought, why cannot we just use it for OD data? So I tried it and it worked. So there are two steps involved. First, we cluster the locations based on distance. It's agglomerative hierarchical clustering. We start with the largest locations at the lowest level and aggregate them, add locations within a certain distance to the cluster, and do it for multiple zoom levels. And the distance for the cluster size depends on the zoom level, map zoom level. Then we, like, to position the clusters, we use the center of mass, weighted by the total flows of the locations. And the next step is to aggregate flows. Once we have aggregated the locations, we can sum up all the flows between the clusters. So we have some locations, they form clusters. Then we create centroids, centers of masses, which are closer to the largest locations in the cluster. Then we aggregate the flows, and that's the resulting flow map. So for the two examples I showed before, it looks like this. More readable, I think. And the internal flows are shown, actually, they are represented by the sizes of the clusters. They add up to the size of the circles. So you see there were lots of flows within this cluster. The good thing is that it's pretty fast, and you can do it for every zoom level, every map zoom level. So you can do something like this. Zoom in and out, and they will expand or collapse, depending on the map zoom level. The author of the library didn't expect this to be used for OD, so he was a bit surprised. Yes, so we got some feedback from a transport analyst about this. Like they mentioned that often shapes which they work with are not uniform. Like here you see an example of census tracts in the US. They are based by population, right? And there are some very small census tracts where the population is high and like huge where there's almost nobody. And this adds some bias to what they do. So doing clustering based on that, based on the distance, would actually help to eliminate bias. And they suggested that we add a slider to interactively select the clustering level, or choose the distance for the cluster size, which we have in our dashboard. There is related work. I'm not the first one who did some clustering on OD data, but it's the first open source library which I know of, which people can use. This paper is interesting because they actually didn't cluster locations, but the flows. They have a quite complex distance measure to decide which flows to cluster together. And the result is somewhat different from what you achieve by clustering locations. Okay, the next dimension I want to speak about is the scalable database. In order for interactive analysis to be useful, the query response time shouldn't be too slow, right? Otherwise, people will not use it. So when we have OD data with attributes, it can grow quite big quite quickly. Like here's an example dataset with only 10 locations and a few attributes with not so many buckets. The dataset has 700 million rows, which doesn't work that well in Postgres, unfortunately. So the two types of queries which we use in our dashboard is one is flow, to get the flows, aggregated flow counts. So in SQL it can be expressed like this. We group by origin and destination and sum all the counts. And another is attribute breakdown to make these histograms or bar charts, category bar charts for attributes. We group by one of the attributes and sum all of the counts for those attributes. So we looked around, evaluated a few databases which would allow us to make these queries perform well. And the one I actually use now is called ClickHouse. It's not very well known, but it's actually a shame because it's good. It's a columnar database for real-time analytics. How is it marketed? It's free and open source. That's important. It supports SQL queries. It's super fast and scalable. There are comparable datasets which we looked at. BigQuery and MapD. BigQuery is the one by Google. It only offers a hosted solution, so you have to upload data to Google, which wasn't an option for us. Also there you pay by the amount of data processed in each query you run, so it can get quite expensive. MapD is a GPU. It's actually renamed now into OmniSci, which Anita mentioned. It's a GPU-based dataset, which is fast, but you have to pay quite a lot for a cluster with GPUs. So it's also quite expensive. It was at least when we evaluated it 2 years ago or so. GeoMesa we looked at, but not detailed enough. After your talk, I think we should look again. We actually use Spark for the data preparation step, but not for the application itself, because Spark is not that well suited for interactive analytics. So what's the difference between column-oriented and row-oriented? Like Postgres is row-oriented. That means that the data is stored on disk in rows, row by row. If you have many attributes and your query only asks for 3 of them or a few of them, you still have to read from disk all of the rows data, which may cost a lot of time if you have many columns in your table. So column-oriented databases are storing data column by column, That's why if you only refer to a few columns in your query, it's faster. And as you saw in the examples I showed before, we only need to query for 2 or 3 columns in our queries. And it's also scalable. You can add more nodes into your cluster to make queries perform faster, because the work will be split between multiple nodes. So actually, the way we store OD data in ClickHouse is very simple. It's one huge denormalized table. We have origin, destination, count, and attribute values. It's not even geographic. An example query, we have a data set with 1.4 billion rows in a cluster of 4 relatively small nodes. The query takes less than 7 seconds to aggregate locations by the origin. Another example is, I just tried on my MacBook. It's a much smaller data set, 17 billion rows, New York taxi data, city bike data. The query took 140 milliseconds. Another example, 4 seconds of aggregation for attribute on the Google cluster. And if we wanted the queries to be faster, we can just add more nodes and they will perform faster. But a few seconds in response time is what we are targeting to support interactive analytics. There have been a few blog posts with detailed metrics, benchmarks for ClickHouse. Mark Litvinchik actually, he made quite a few, he evaluated quite a few databases and on New York taxi data. And he writes that CPU is the fastest, the only one which outperformed a GPU-based database. And it's a shame that it's not widely known and used. So we actually open sourced and published a demo app which combines the 2 techniques I was talking about. The clustering, zoom-dependent clustering, and the ClickHouse as a database backend. It is a demo. You can play with it. You can use the code. And I hope it inspires people to build something with it. We actually don't use any geographic functions at the moment of ClickHouse, but it has some. It has a few, like you can calculate great circle distance, find points in a polygon, and it has some support for geohashing. There's another interesting blog post by Carto. They used ClickHouse for geographic data. I think it was New York taxis also. And then they used quad key, which is a similar technique as to geohashing. You can put together 2 coordinates, let alone into 1 integer, which makes it faster to query for certain areas, geographic areas of your data. Yeah, so they just added, they have let alone in their table and quad key, and the query could look like this. You can have a range of quad keys in a query to limit the geographic area which you are looking at. So it's even if the database didn't have any geographic support, you can still do some geographic stuff. Related work, New York University, published by people from the New York University. They looked at New York taxi data, and they actually developed their own database with some special indexing to support different kinds of queries. Sorry, I just have too many slides, I have to skip them. If you feel dizzy, shout. So, future work. Like currently, there is still some limitations on the number of locations we can support in one dashboard, because we don't tile them, we load them all at once. And when you zoom in to the finest grained zoom level, there can be too many locations and too many flows between them. So it would be at least something to explore, to implement tiling with geohashing and clustering in order to split the data which we are loading into chunks, which are actually, so if this is the visible viewport in the browser, we would only need to load the blue arrows and not the black arrows into the view. And in order to, like, these are the tiles if we use tiling, which are crossing the visible viewport. We would only need to query data for these tiles. And in order to efficiently query data from these tiles, geohashing would help. And clustering would help when you zoom out. You need to represent data as a summary and not all the individual flows in order for it to perform well. So with this approach, we could support virtually unlimited numbers of locations and flows between them. Thank you. So a lot of this work is available as open source projects. Like FlowMapBlue is the tool for non-programmers to visualize OD data, which includes clustering out of the box. FlowMapQuery is this demo app for ClickHouse and clustering, where you can also filter by attributes. And FlowMapJL is a library, JavaScript library for rendering flow maps.
Thank you very much. That was super interesting. Who has heard of ClickHouse before?